If you know me at all, you'll know that I love math. If you know me even better, you'll know that I love The Legend of Zelda. Making connections between the two is like a dream come true, so when I was asked to teach a topic in a creative way, I thought long and hard about how to make my statistics knowledge relate to some of my favorite video games. I finally settled on one of my favorite topics from a truly incredible game. So today we're going to talk about significance testing, sometimes also called hypothesis testing, using data from the Wind Waker HD. If you're unfamiliar with the game, I'll quickly cover the topic of choice. On Windfall Island, sitting roughly due north in the overworld, there's a building that hosts a minigame known as the Windfall Auction. Players can bid on different items that appear, using strategic bid increases to win. But the math behind that is an entirely different ballgame. My focus today is going to be on the different items and the frequency in which they appear on the first entrance to the auction house. The game itself does allow you to play multiple times and acquire all of the items, but we're just focusing on the initial one that appears for the sake of simplicity. For modern-day games, random elements, such as auction items, are determined using code that produces a series of values. This is affectionately referred to in video game communities as RNG, short for Random Number Generator, which is the system that produces these values. Let's assume that the system determines values that are truly random, making the probability of receiving each item equal. This means that the 5 items, which are 2 different treasure charts, a heart piece, a joy pendant, and the swift sail, all have a 0.2 probability of appearing on the first try. For the sake of the problem, I'll focus on the swift sail, since it is generally the most sought-after item from the minigame. In this example, let's say that the players believe that the RNG is actually skewed to favor other items over the swift sail to increase playtime. Data collected from various content creators supports this, with the swift sail being found at the auction house for 7 out of the 50 initial visits recorded. Using the beloved state, plan, do, conclude model, let's approach the problem and determine if players really are getting scammed. Based on the RNG, the swift sail has a hypothetical probability of 0.2 to appear at your first entrance to the auction house, which gives us the population proportion of p is equal to 0.2 to use to set our null and alternative hypotheses. In this case, our null hypothesis is the default answer, that the RNG is not skewed to favor any particular item. Our alternative hypothesis is then going to be the opposite of our null. The RNG does favor other items over the swift sail on the first visit to the auction house. Now that we have defined our hypotheses, let's represent them mathematically with probability notation. It's important to remember that the null hypothesis will always be set equal to a value, and that the alternative will always be either greater than, less than, or not equal to that same value. The last portion of the state segment requires us to state the parameter that we're observing. So let's do that now. Now that we know what we're trying to prove or disprove, let's make sure that we can actually run our test. We have to check 3 conditions for significance tests: randomness, independence, and normality. Randomness has already been taken care of, since we're testing an RNG element and the gameplay videos were all selected at random. Independence is going to be checked most of the time using the 10% condition, which states that the sample must account for less than or exactly 10% of the population. In this case, our sample size of 50 first-time visits to the auction house is going to be less than or equal to the total number of times the auction house has been first entered. Unless, for some reason, it's been visited less than 500 times globally, and I know for a fact that that's not true. The last condition that needs to be checked is normality, which can be done in 2 different ways. If you're dealing with means, you would want to use the central limit theorem, which says that n must be greater than or equal to 30, where n is your sample size. Since we're dealing with proportions, we'll use the second of the 2 conditions, large counts. For large counts, the sample size, n, times the estimated population proportion, p, must be greater than or equal to 10, and the sample size times 1 minus the estimated population proportion must also be greater than or equal to 10. To put it more simply, here are the 2 equations we need to use to check large counts. Remember that both equations must be true in order for us to test our hypotheses. Without the conditions, nothing is guaranteed to be normal, and our answers would be meaningless. Combining all of the results, here are the conditions we have. As you can see, all 3 of the conditions have been met. For this example, I went through with checking everything, but it won't always be required. If the problem states that the conditions for inference have already been met, you can skip this part of the process. The last thing we're going to need to do for our plan segment is state what kind of test we're going to perform. There are, once again, 2 different ways that this can be done. You can either name the test with words, or you can simply just state the standardized test statistic formula. That's going to be either a z-score or a t-score. The test statistic will give us a standardized measurement, which means that we'll be able to compare it using standard deviations from the mean. Since we're dealing with proportions, we're going to be using a z-score for this example. And yes, you guessed it, a t-score would be used for means. You can also choose to combine those 2 formulas into one, but I'll be dealing with them separately, since I find it easier to work with. Now we know for sure what we're doing and that we can do it, so it's time to start doing some actual math. Based on our data, here's what we know so far. I'm going to start by finding the standard deviation using the formula that I had listed in the plan section before beginning the standardized test statistic, since, of course, we'll need the standard deviation to find our z-score. I'm going to go ahead and show all of the values rounded to 4 decimal points, but be sure to keep the exact numbers stored in your calculator and use those to find the remaining values. Speaking of remaining values, let's find the z-score now that we have what we need. At this point, the question that comes to mind should be, now what? We calculated the standardized test statistic and everything needed to find it, so are we done? Short answer, nope. The standardized test statistic is only going to produce a value which we'll need to compare to a normal probability distribution. The last step of the do process is to actually find the p-value, which, by the way, is not the same as the population proportion, p. The p-value is defined as the probability of obtaining the sample results or more extreme given that the null hypothesis is true. What might that mean? In the context of this problem, the p-value is going to represent the true probability of getting a sample where the Swift sale appears on the first try 14% of the time, or less often, assuming that the RNG isn't skewed against the Swift sale. Testing for proportions means that we'll be using a normal cumulative distribution function, better known as normal CDF. If we were talking about means, we'd actually use a different CDF, the t-CDF. Keep in mind that we're dealing with a z-score, and z-scores have a mean of 0 and a standard deviation of 1. We'll be using those as we enter the function into our calculator, like so. And finally, we're done with all of the hard stuff. We've stated our goal, planned the procedure, and done the calculations. So what's left? To wrap it all up, we're going to interpret the results for our conclude segment. Before I do this, I'm going to introduce one more value. Most people will include it in the state portion, but I usually only reference it at the end, since it's not really relevant until we obtain a p-value. This value is our significance level, also called the alpha level. The alpha level is going to serve as the threshold for the p-value, and it's what we'll be measuring the p-value against. Because the problem didn't give a different alpha level, we're going to use 0.05 by default, but increasing or decreasing our threshold may change the conclusion. For now, though, we'll stick with the 0.05 significance. Looking at the p-value compared to the alpha level can tell us one of two things. If the p-value is beneath the alpha level, we would reject the null hypothesis due to statistically significant evidence to support this. If the p-value is above the alpha level, our result is plausible, so we would fail to reject the null. Looking at our numbers, 0.1444 is greater than 0.05, which means that we'll fail to reject the null hypothesis. Using this template, let's wrap up all of our math into something more coherent. Adding in all of the numbers and the correct conclusions we've drawn from them, it should look something like this. And don't forget to add the appropriate context. And at last, we have our answer. The RNG for the minigame is actually relatively fair. That's probably not what some people wanted to hear, and it certainly won't make you feel any less unlucky the next time you try your hand at the Windfall Auction. I had a great deal of fun with all of this, so I hope you, too, enjoyed the math behind the Wind Waker HD.